Welcome to this lecture. We are going to talk about the plate fin type heat exchangers, and we were discussing about the analysis of plate fin type heat exchangers, where we have analyzed the fin equation and we tried to differentiate between the different type of flow regimes, not regimes, rather the temperature domains or the temperature configurations that is possible in a plate fin type multi-stream exchangers. And in that context, we have seen that the plate fin type heat exchanger, where there may be multiple fluid streams, and we have to analyze this kind of heat exchanger, where we were attempting basically a type of what is called the simulation problem we are trying to solve. And here we have seen that we have the fluid stream going in at T in and it is coming out at T I out, whereas this is for the ith fluid stream, and this is the T W I minus 1 is the wall temperature, and this is the T W I. This plate is at temperature T W I, and we have this plate temperature at T W I minus 1. So, this is the generalized configuration, where we may have, say, this is the ith fluid stream, and we have this I minus 1th fluid stream, this is I plus 1th fluid stream, and this wall temperature is designated at T W I minus 1, and this wall temperature is designated as T W I. So, in this generalized configuration, we now want to find out how this temperature of the plate and the fluid streams are correlated, and in that context we have solved the basic fin equation connecting between the two walls. Maybe we have solved it as considering it to be T A and T B in the generalized form, but here it is in the more generalized form of T W I minus 1 and T W I. So, here basically T W I is T B and T W A is T W I minus 1. So, this correspondence is there. So, now we have seen that if we are solving that basic fin equation, where the walls are at T B and T A, and we find out the heat transfer equation for this fin joining these two parallel plates or the separating plates, and the fluid flowing on top of it is T 0 at a temperature T 0, and it has already been assumed, though we have not explicitly said, that the fluid is not undergoing any phase change. So, now in this situation, what we have seen that if the fluid temperature and the plate temperatures are like that, we can have we will come back to this again, that generalized configuration. Before that, we just want to recapitulate what we have learned in the earlier class, where we have seen that this Q A, the amount of heat getting transferred from the wall to the fluid, where the fluid temperature is T 0 and the wall temperature is T A, and this is basically Q B. It is not looking properly. Okay. So, this is Q A and this is Q B getting transferred from the wall to the fluid, and here this is from this wall T A to the fluid, where the fluid temperature is T 0, and this wall is at a temperature T B. This is where it is, its temperature is at this point is T B. So, now in this context, we have seen if r equals to 0 or theta b by theta a, that is equals to r and that is equals to 1, we have seen that this x becomes half. Where do we get this? We get this from this relation, that if there has to be a minima, then this minima will give a criteria like e to the power 2 m x is equals to this correlation. And here in this context, if we put r equals to 1 or theta b by theta a equals to 1, we find that x becomes half. So, that means when these two temperatures are the same, we have a minima at the middle or at the center of this plate. Now, if this is not equals to 1 or if it is having some other value, and we were talking about the different possibilities, in that context we have seen that sometime it may be possible that the location of this extremum may go beyond the physical boundary. Physical boundary mean that this is the fin, these are the two separating plates, and this minima may occur beyond the physical boundary of this one, either on this side or on this side, depending on the value of r. And we try to analyze the different situations. So, in that context we have seen that we have, first of all, we have evaluated this q a and q b, and we have seen these are the expressions for q a and q b. It is important, and we will look into this again when we talk about the other configurations or possibilities or of the temperature of the plate and the fluid. So, now what is the other possibility that we have already talked about in the last class? It was such that in case this r equals to exactly 1 by cos hyperbolic m l. So, in that situation we find that the extremum is occurring at the fin base of the q b. And now, if we find that if this r equals to 1 by cos hyperbolic m l, it is not only giving the extremum at the fin base of the other plate, we are also finding that this q b will change its direction. So, now this heat is no longer, earlier we have seen that heat was coming from the plate to the fluid. Since that is expected, because the plate temperature is higher than the fluid temperature. So, this fluid is supposed to give, this plate is supposed to give heat to the fluid, but here we are finding that if it is such that the situation is such that 1 by r becomes, when r becomes 1 by cos hyperbolic m l, it may so happen that r is 1 by cos hyperbolic m l, you will find that x is not only L, but this fluid is, this plate is no longer giving heat to the fluid, rather this heat q a has already been, which is having origin from this fin base, it is coming to the fin base B. So, this is nothing but what we have said, that transverse conduction of heat, and sometime we have to face this situation depending on the different fluid stream temperature and the plate temperature. So, now here also we find that if we analyze this q a and q b, how did we do that? You may remember that q a has been obtained by integrating or calculating the heat transfer within this length x and this L minus x, and we have done the integration over this part and this part. Separately we have calculated, and that is q a is from here and q b was from here. And according to this, even if it is r equals to 1 by cos hyperbolic m l, we will find that for this length x, we have q a amount of heat equals to this much, and L minus x over this length L minus x, we will have this heat transfer q b. Now, what happens if r is still smaller, this cos hyperbolic ml is more than 1, and we find that this becomes it is exactly I mean less than 1, and this is in this situation what happens, this x becomes x goes beyond the physical boundary of this physical plate. So, in that case also you will find that these two equations are taking care of that, even if there is axial conduction transverse conduction of heat, it is automatically being taken care. Now, there may be another situation what we have talked in the last class, that there may be a situation where the temperature of the fluid is intermediate to the plate temperature. So, here this is T A, this plate is at a temperature T B corresponding to this one, and the fluid temperature is intermediate to T A and T B. So, if we have a situation where this T 0 is at the middle of T A and T B, so we will find some position where this temperature difference, or this theta x, which was T minus T 0. So, this will vanish at some point intermediate, and that will be equal to say 0, or as it is as we have said, it is vanishing. So, if we put this condition and this is theta x, already we have obtained the fin equation, and if we equate it to 0, we will have a correlation relation for the x and the length at which it is having theta x equals to 0 is given by this relation. So, if it is so, then you will find this is not exactly what we have obtained earlier. The earlier expression, if you remember, it will be something like this. It was e to the power 2 m x is equals to e to the power m l minus r divided by r minus e to the power minus m l. This was the expression when the minima was lying in between or beyond the physical boundary of the fin. But in contrast to that, here what we have is some relation. This is like this. So, here the corresponding the x at which this fin, from here to here, the heat is coming from this wall to the fluid, and between this section the fluid to this wall, the heat is coming. So, we have two distinct region to calculate this Q A and Q B, and here the x is given by this relation. So, this is not exactly similar to the earlier situation, and its reflection will be there in the amount of Q A, that is there will be a term like minus psi and plus psi. So, these terms will be added to this, so that you find that this Q A plus Q B that remains the same as earlier, because these two terms will cancel each other when we combine together, that or Q T that remains same, but this individual heat transfer Q A from the plate and from the plate B, that becomes slightly different. And in fact, we need both Q A and Q B separately to estimate the plate temperature. So, it is important. Now, it has become case dependent, that if the R equals to less than 0 or T 0 is intermediate to T A and T B, we find that we have to keep it in mind that to take care of the transverse heat conduction from one plate to the other plate, there has to be some kind of additional parameter psi that has to be added or subtracted with the appropriate one, with the appropriate Q A or Q B. So, this is an additional task, but how to overcome that one has also been suggested by BSB Prashad, and we will find that there is an alternative way of calculating this Q A and QB. So, we will try that one. And how is that? I mean, since we know the temperature profile of this fin, I mean fin temperature profile already we have calculated, that is the theta x we have solved. So, we know the temperature profile. So, another way of calculating the QA or QB is from the fin equation, and we will look into that in the next slide. So, we find that we can find out I mean all the situations we will see one by one, and we will find that this heat transfer from the Q A. Now, earlier we were telling it as Q A only, now we are telling it as Q A fin base. So, that means earlier we were trying to estimate the heat transfer, and where we have try to locate where is the minima. So, that is the distance x. If it is located at a distance x, then we integrate and find out Q A over this length. Now, this Q B we have calculated over this length L minus x, but here how are we estimating this Q A, and how we are differentiating it? It is differentiated as Q A fin base, and that is equals to minus k T dt dx. Please mind that this k T, it is only we have not considered the other dimension or this length dimension of the fin. This is basically a heat transfer per unit length. So, this is k T into d theta x dx at a location x equals to 0, and we can try to find out this Q B at the fin base of B, and we designate it as Q B fin base, that is why F B, and that is similar to k T d theta dx at x equals to L. So, this is x equals to L. So, here exactly we will find that this expression is nothing but the expression Q A, and this expression is nothing but Q B. But why did we do that? Is there any special significance that Q A, F B and Q A are equal? It is expected that the fin base heat transfer and the heat transfer taking place through this fin is supposed to be the same, but we will find the difference later on. So, here in this case, as such, when r is equals to 1 and x is half, or for other relations where we know the fin extrema is located within this region, or it is slightly on this side or on this side, this expression is remaining valid. So, now let us go look into the other situation where as we are saying that it is beyond the physical boundary of the fin. So, corresponding to that situation, we have r equals to 1 by cos hyperbolic m l, and this also we have analyzed earlier. Now, in this situation we know that at x equals to L, corresponding to r equals to 1 by cos hyperbolic m l, that gives the minima at x equals to L. But if we find the heat transfer at the fin base expression like minus k T dt dx at x equals to 0, that is at x equals to 0 on this side, and fin base at d theta x dx at x equals to L on this side, that will be this one. And you see again here this Q A is equals to Q A fin base, and Q B is equals to Q B fin base. So, here also we do not find any difference between the fin base heat transfer or the heat transfer from the fin length calculation. But what is about the situation when we go to the other when we go to the next case where we find that this temperature is intermediate to this plate temperature T A and T B, and in this situation the R value is less than 0, and this is corresponding to the situation where x is at some intermediate point and giving correlated to this temperature ratio ratio R by this relation. Here you see this fin base Q A and fin base Q B, they are not similar to the Q A and the Q B expression that we have obtained based on the length. Because this length was different, the x that we have estimated for this Q A was taken from this x, and that is why our Q A and Q B expression was either having a plus minus psi term. But here in this case, since this is completely based on the fin base heat transfer, and that is automatically, this expression is automatically taking care of the axial conduction, transverse conduction of heat taking place from one plate to the other plate. So, that means while analyzing the plate fin type heat exchangers, when there would be multiple fluid streams or multiple arranged in multiple layers, what we need to look into, we cannot separately keep notice whether there is a kind of transverse conduction or not, because it is not possible at some intermediate location what is happening between the plate and the fluid temperatures. So, automatically the equations should be framed such a way that that effect is taken care. So, for that we find that if we are taking this Q A fin base expression, then it is always taking care of that heat transfer, that is this is equals to this, and that is taking care of the transverse conduction from one fin to the other fin without bypassing the fluid, or we call it a bypass heat transfer. This is very frequently it is a common phenomena in multi-stream plate fin heat exchanger. So, that will be taken care automatically by this expression. So, we understand that this particular expression we will be using for doing the multi-stream plate fin heat exchanger analysis. So, but expression wise it looks this for the Q B fin base, and this is the expression what we get for the Q A. So, now based on this information we will again go back to our where we have started with, where in a generalized heat exchanger configuration, where there may be n number of fluid streams and n plus 1 number of wall temperatures, then we have this in a generalized condition we have this is the inlet temperature and this is the outlet temperature of fluid stream surrounded by these two walls T W I and T W I minus 1. Now, here in this context we will write that we have already told that if there are n number of fluid streams, we have n number 1 number of wall, and we have altogether 2n plus 1 number of equations and unknowns are there. So, we have to frame those 2n plus 1 number of equations. So, first of all what we will like to do is that we will take a energy balance over this ith number of channel, where this is entering at T in and moving out at T out, and what are the heat transfer that is going to take place. So, some amount of heat will be coming from here, some amount of heat will be coming from this, and the fluid will be receiving that amount of heat and it will come out. So, this together combined heat Q A plus Q B that becomes Q T, and that we have seen as constant, and we will take care of, I mean this, if we take an energy balance, we will look into that in details. So, in the next slide we will now go to this, that when we do the heat transfer, or I mean energy balance, and in this for the ith fluid stream, we find that the heat is getting transferred from the primary surface, as well as heat is coming from the fin. So, both for this type of fin, and both, I mean for this fin also, either it is A and B, and the separate, I mean this primary surface area. So, this is the primary heat transfer surface area, contribution from the primary heat transfer surface area, and of the ith plate, this is H I, A primary I, and this is the difference in temperature. This is, say, if we consider it to be the T I, which is an average between T in and T out, and then it is T I minus T W I, and then we have, this is for the T W I. So, this is this temperature difference between this fluid, and this is this one, the other part, T W I minus T W, sorry, T W I and T W T I, and the corresponding surface area and the heat transfer coefficient. And then we have this Q T, as we have said that Q T is nothing but Q A plus Q B, and this is eta half, and that is just in all the cases, whether it is having transverse heat conduction or not, we can write this total heat transfer to be H into fin length, and then theta A and theta B and eta half. So, this theta A is basically T W I minus 1 and T I, and theta B will be T W I minus T I. So, that is the energy balance we will have for the fluid stream, and that will be equal to the heat capacity, the mass flow rate multiplied by the C P, and T out minus T in. So, that will write or give the total energy balance equation for this ith fluid stream. Now, we need to look into the heat balance on the wall T W I minus 1. So, now we have the contribution from the primary surface, and this primary surface on the B side fin, and primary surface on the A side fin. We designate this fin as A and this is as B. So, now we have this overall energy balance. If we take around this plate, we find that half of H I minus 1, I mean that is the H I minus, this is I minus T I minus 1 th fluid, and its temperature is T I minus 1, this side is fluid is I minus 1, and this is ith fluid. So, we have the heat transfer between this surface, I mean this primary surface area on the I minus 1th side, heat transfer surface area in heat transfer coefficient, temperature difference between the fluid and the wall, and then the primary heat transfer contribution on the wall side. So, and then we have this contribution from the B side fin, and the heat transfer from the fin base of the ith minus, I mean I minus 1th side fluid, and then we have the heat transfer Q A for the A side and the fin base, as we have decided, on the ith side fluid. So, that is equals to 0. So, like that we have to, this is the I mean equation for the wall of I minus 1th one, and this is the heat transfer. We have also looked for the I mean already we have figured out or estimated the heat transfer for the ith fluid. So, like that we will have then 2 n plus 1 number of fluid streams, and and I mean sorry n number of fluid streams and n plus 1 number of walls. So, altogether 2n plus n number of such equations we would be able to frame, and those becomes algebraic equation. Then we need to solve those equations to find out the wall temperature as well as the fluid exit temperature, and that is exactly what we were looking for to simulate the plate fin type heat exchangers. So, once we know the exit temperatures of the fluid streams, and we would be able to calculate what is the heat duty of these brazed aluminum plate fin type heat exchangers. So, thank you for your attention.